On May 26, 2026, NASA awarded the first construction contracts for a permanent moon base. Not a visit, not a flag and footprints, a place where humans would live and work continuously at the lunar South Pole for years. The agency has committed $20 billion in a three-phase plan stretching into the 2030s. The animations look inspiring. The press conferences sound confident, but almost nobody is talking about what actually happens when you try to keep people alive on the moon permanently. The dust destroys everything it touches. The darkness lasts for hundreds of hours. The radiation never stops. And every system you build begins failing the moment it arrives. This is why building a moon base is far worse than you think. If you enjoy deep explorations of the hardest problems in space, consider hitting that like button and subscribing. It genuinely helps this channel keep making content like this. Now, get yourself comfortable. Let's begin. On March 24th, 2026, NASA held a press event it called Ignition. The name was deliberate. The agency announced a complete restructuring of its Artemis program around a single goal that had been discussed for decades, but never funded with this level of commitment. The United States would build a permanent base on the surface of the moon, not a temporary outpost, not a short sortie camp, a phased, continuously expanding installation near the lunar South Pole designed to support human beings living and working on another world for months and eventually years at a time. The price tag was $20 billion over 7 years. The contracts would flow through commercial partners. The construction timeline would stretch across 3 phases, beginning with robotic scouting missions and ending with sustained habitation infrastructure sometime in the early to mid-2030s. Administrator Jared Isaacman framed it in language that left no ambiguity. America would never again give up the moon. Within weeks, the plan accelerated further. On May 26, 2026, NASA awarded the first moon base contracts to Blue Origin, Astrolab, Lunar Outpost, and Firefly Aerospace. Blue Origin would provide the Mark 1 Endurance lander for Moon Base 1, targeted for launch no earlier than fall 2026. Astrolab and Lunar Outpost would build the rovers. Firefly would handle orbital relay infrastructure. The agency unveiled a vision not of a single habitat module sitting alone in a crater, but of a distributed network of assets spanning hundreds of square miles across the South Pole region. Habitats, science stations, power units, roads, communication relays, rover garages, and hopping drones called Moonfall that could scout terrain autonomously. The scale was not modest. It was the most ambitious surface infrastructure plan NASA had announced since the Apollo program, and there was momentum behind it. Just weeks before the May contracts, Artemis 2 had completed its mission. 4 astronauts had flown around the moon and returned safely, validating the Orion spacecraft, the Space Launch System rocket, and the deep space life support systems that would underpin every crewed mission going forward. Artemis 3 was restructured as an orbital docking test in 2027. Artemis 4, planned for 2028, would attempt the first crewed lunar landing since 1972. After that, NASA intended to land crews on the moon every 6 months, building capability and infrastructure with each visit until the base became self-sustaining enough for continuous occupation. The coverage was enthusiastic. Animations showed gleaming habitats perched on crater rims bathed in golden sunlight. Infographics mapped the 3 construction phases with neat arrows and confident timelines. Social media imagined pizza restaurants on the moon. The narrative was clear. Humanity was going back, and this time we were staying. Almost nobody paused to ask the harder question. Not whether we could land on the moon again. We clearly could. Not whether we could build a structure there. Engineering firms were already designing them. The harder question was what happens after the structure lands. What happens when you try to keep it functioning? What happens when you try to keep people alive inside it? Not for a week, not for a visit, but continuously across months and years, in an environment that attacks every material, every seal, every machine, every biological system, every day, without pause. That question changes everything about how a moon base should be understood, and the answer is far worse than the press conferences suggest. To grasp why, you need to understand what the moon actually is as an engineering environment. not the poetic moon of photographs and mythology. Not the simplified moon of school textbooks, the real moon, the physical moon. The moon that Apollo astronauts experienced firsthand and came back warning about. The lunar surface has no atmosphere. This is stated so often that it has lost its power. People hear it and think it simply means there is no air to breathe. That is the least of the problems. No atmosphere means no air pressure. Every habitat on the moon is a pressure vessel, an inflated structure holding breathable air against the vacuum of space. If the wall of your house on Earth develops a small crack, you get a draft. If the wall of your habitat on the moon develops a small crack, you get explosive decompression. There is no margin, no forgiveness. Every seal, every joint, every window, every airlock mechanism is a potential point of catastrophic failure, and every single one of those components is under constant mechanical stress from the pressure differential between inside and outside, every second of every day, for as long as the base exists. No atmosphere also means no thermal buffer. On Earth, the atmosphere acts as a massive heat transfer medium. Air carries warmth from sunny areas to shaded areas, wind mixes temperature layers, clouds moderate solar input, humidity stores and releases thermal energy. None of that exists on the moon. Heat transfer on the lunar surface is limited to two mechanisms: radiation and conduction. There is no convection, there is no insulating blanket of gas softening the temperature swings. The result is a thermal environment so extreme it challenges every material and every machine ever designed for human use. At the lunar equator, surface temperatures swing from roughly 127 degrees Celsius in direct sunlight to minus 173 degrees Celsius during the 2-week lunar night. That is a range of 300 degrees Celsius, cycling every 29.5 Earth days. At the South Pole, the situation is different but not easier. The sun never rises high above the horizon. Elevated ridgelines near craters like Shackleton receive near-continuous illumination for much of the lunar year, which is why NASA chose the South Pole in the first place. But even the best South Pole sites experience periodic shadow. Some candidate locations endure darkness lasting several consecutive Earth days. Others face intermittent shadow cycles driven by the moon's slight axial tilt and local topography. And nearby, in the permanently shadowed crater floors where the precious water ice sits, temperatures plunge below minus 200 degrees Celsius. Some measurements place them below minus 230 degrees Celsius. These are among the coldest naturally occurring temperatures in the inner solar system. No atmosphere also means no protection from radiation. On Earth, the atmosphere provides shielding equivalent to roughly 10 meters of water above your head. The planet's magnetic field deflects the majority of incoming charged particles before they even reach the atmosphere. On the Moon, there is no magnetic field worth measuring and no atmosphere worth mentioning. Every particle of galactic cosmic radiation, every proton and heavy ion, accelerated to near light speed by distant supernovae, arrives at the lunar surface with its full energy intact. Solar particle events, sudden bursts of energetic protons ejected by solar flares and coronal mass ejections, hit the surface unimpeded. The first direct measurements of radiation dose on the lunar surface came from China's Chang'e 4 lander, which recorded an absorbed dose rate roughly 2 to 3 times higher than what astronauts experience aboard the ISS in low Earth orbit. On the unshielded lunar surface, a human being would accumulate approximately 400 millisieverts of radiation exposure per year from galactic cosmic rays alone. NASA's career dose limit for astronauts is 600 millisieverts. A single large solar particle event could deliver a lethal dose in hours to an unshielded person. And no atmosphere means no protection from micrometeorites. Tiny particles of space debris that would burn up harmlessly in Earth's upper atmosphere strike the lunar surface at speeds reaching 70 kilometers per second. Over time, these impacts erode exposed surfaces, pit optical coatings, degrade solar panels, and create additional fine dust that adds to the already overwhelming regolith problem. This is the environment into which NASA plans to place a permanent base. Not for a 3-day visit as Apollo managed. Not for a week-long sortie where astronauts live out of their lander and leave before anything has time to fail. A permanent installation that must survive and operate through thousands of thermal cycles, continuous radiation bombardment, relentless dust intrusion, micrometeorite erosion, and the mechanical stress of maintaining atmospheric pressure inside a sealed structure sitting on the surface of an airless world. The distinction between a short visit and permanent habitation is not a difference of degree. It is a difference of kind. Apollo succeeded precisely because it was brief. The astronauts landed, performed their tasks, and left within 3 days. Their spacesuits degraded visibly during that time. Dust abraded the outer layers, clogged joints, scratched helmet visors, and infiltrated the cabin despite every precaution. Astronaut Harrison Schmitt reported what he called lunar hay fever, a respiratory reaction to inhaled regolith particles that affected all 12 humans who walked on the moon. The vacuum seals on sample containers were compromised. Boot soles eroded measurably. All of that happened in less than 72 hours. Now extend that to 6 months. Extend it to a year. Extend it to the continuous occupation NASA envisions for the 2030s. Every problem Apollo encountered becomes not merely worse, but qualitatively different. Dust does not just coat your spacesuit during one excursion. It infiltrates your habitat through every airlock cycle, accumulates in ventilation filters, abrades mechanical components, shorts out electronics, and embeds itself in human lung tissue over months of chronic exposure. SEALs do not just hold for a 3-day mission, they must hold for years while being ground down by temperature cycling, radiation degradation, and abrasive particles finer than talcum powder but sharper than ground glass. Power systems do not just need to last through one sunlit landing. They must operate continuously through cycles of illumination and shadow, surviving thermal shock, dust coating, and mechanical wear without any possibility of a repair truck arriving from the nearest service center 240,000 miles away. This is the conceptual shift that the moon base conversation almost always fails to make. The public discussion treats a moon base as a construction project. You design a habitat, you launch it, you land it, you move in. Like building a house in a harsh climate. But a moon base is not a house. It is a submarine. It is a sealed life support vessel surrounded by an environment that is trying to kill everyone inside it through a dozen simultaneous mechanisms. And unlike a submarine, it cannot surface. Unlike the ISS, it sits in a gravity well that makes evacuation slow and expensive. Unlike an Antarctic research station, it cannot receive emergency resupply by airplane. The moon base must keep itself alive or its crew dies, and the environment works against that survival every second. NASA understands this, at least in its engineering documents. The phased approach announced in March 2026 is explicitly designed to build capability incrementally, testing systems robotically before trusting them with human lives. Phase 1, running through 2029, focuses on robotic scouting, environmental measurements, technology demonstrations, and cargo deliveries to the South Pole. Phase 2, spanning 2029 to roughly 2032, begins building permanent infrastructure, including power systems, pressurized rovers, and initial habitat elements. Phase 3, extending into the mid-2030s and beyond, targets sustained human presence with long-duration crew rotations. The phase timeline is sensible engineering, I think. It acknowledges that you cannot simply drop a habitat on the moon and move in. You must first understand the terrain at a level Apollo never achieved. You must characterize the dust environment, map the thermal conditions at specific sites over full lunar years, measure the radiation environment with modern instruments, test whether construction materials survive long-term exposure, and verify that power systems can sustain operations through darkness. Each phase depends on the success of the previous one. Each phase carries risk, but the phased approach also reveals something the press conferences do not emphasize. The timeline stretches across an entire decade. The base will not be operational until the mid-2030s at the earliest. That is not because the engineering is simply large-scale. It is because the engineering is genuinely difficult in ways that have no precedent in human spaceflight. No human being has ever spent more than 3 days on the lunar surface. No piece of human-made equipment has been designed to operate continuously in lunar surface conditions for years. No life support system has been tested against chronic dust infiltration, simultaneous radiation exposure, and extreme thermal cycling in 1/6 gravity over long durations. Every system the base requires must be either invented, adapted from systems designed for fundamentally different environments, or tested for the first time on the Moon itself. The South Pole location helps in specific ways, and NASA chose it for good reasons. Crater rims near Shackleton and other polar formations sit at elevations where sunlight grazes the surface almost continuously during much of the lunar year. This near-constant illumination provides the best solar power conditions available anywhere on the Moon and keeps surface temperatures more moderate than equatorial sites. Nearby, permanently shadowed craters contain water ice that has been accumulating for billions of years, shielded from sunlight by crater walls that never see the sun. That ice represents a potentially transformative resource. Water can be split into hydrogen and oxygen, providing breathable air, drinking water, and rocket propellant. If ice extraction proves feasible at operational scale, it could dramatically reduce the mass that must be launched from Earth for every mission. But the South Pole also introduces its own problems. The sun never rises more than a few degrees above the horizon. Lighting conditions are permanently oblique, casting long shadows that shift slowly as the Moon rotates. Navigation and surface operations become difficult in this perpetual twilight. Communication with Earth is complicated by more than just the low sun angle. At the South Pole, the Earth hangs very low on the northern horizon, sometimes barely above it depending on the exact site. Local terrain frequently blocks the line of sight between a surface antenna and Earth. A crew member working in a crater floor, or even behind a modest ridgeline, loses direct contact entirely. This means the base cannot rely on a single fixed antenna, the way the ISS relies on its direct link through tracking and data relay satellites in geosynchronous orbit. The Moon base needs relay infrastructure, either satellites in lunar orbit, or a network of communication towers placed on elevated terrain features to maintain continuous contact with mission control. Without that relay architecture, there will be periods when the base is out of contact with Earth. For a robotic outpost in Phase 1, intermittent blackouts are manageable. For a crewed base in Phase 3, losing communication with Earth during a shadow period when power is most fragile and emergency risk is highest creates a scenario where the crew faces simultaneous power stress, thermal danger, and communication isolation. Every emergency protocol depends on real-time coordination with mission control. Every medical emergency relies on ground-based flight surgeons providing guidance. Every anomaly resolution procedure assumes the crew can consult engineering teams on Earth. If communication drops during the exact window when something goes wrong, the crew is genuinely alone, making life or death decisions with only the expertise present inside the habitat. Building the relay infrastructure to prevent this is part of NASA's plan. Firefly's contract specifically includes orbital communication relay assets, but those assets must be launched, deployed, and maintained in lunar orbit, adding another layer of hardware that can fail, that costs money, and that must be replaced when its operational life expires. The communication problem does not end with a single satellite launch. It requires a sustained orbital infrastructure program, running in parallel with the surface base construction, each dependent on the other, each consuming budget and mission bandwidth. The permanently shadowed craters where ice sits are not just dark, they are among the coldest places in the solar system, places where temperatures approach those of deep space. Any equipment sent into these craters must operate in conditions that would shatter most conventional materials, and the ice itself remains poorly characterized. Orbital instruments have confirmed its presence but cannot yet determine whether it exists in concentrations rich enough to be worth mining, or in deposits so sparse that extraction would consume more energy and equipment life than the water is worth. The answer to that question determines whether the South Pole's greatest asset is a transformative resource or a logistical mirage, and the answer will not come until machines actually dig into those crater floors and measure what they find. The South Pole also concentrates the base's infrastructure into a geographically constrained region. The sites with the best illumination are limited ridgelines and elevated plateaus. The sites with water ice are nearby crater floors. The sites with acceptable communication geometry are specific high points. This means the base cannot spread freely across the surface. It must cluster its assets along favorable terrain features, creating logistical bottlenecks and limiting how far operations can extend without relay infrastructure. The physical scale of these favorable zones is smaller than most people imagine. Orbital mapping by the Lunar Reconnaissance Orbiter has identified the best illuminated sites near Shackleton crater, including the connecting ridge between Shackleton and de Gerlache craters and elevated points near Malapert Mountain. These sites receive sunlight for 80 to 90% of the year, but the zones where illumination, stable footing, acceptable slope angles, communication line of sight, and proximity to shadowed ice deposits all converge simultaneously are remarkably narrow. Some candidate building sites are ridgelines only a few hundred meters wide. On these ridgelines, the base must fit its habitats: solar arrays, thermal radiators, rover parking, construction staging areas, and eventually a nuclear reactor with its 90-meter exclusion zone. Every asset placed on the ridge competes for the same limited real estate. A rover driving between the habitat and a solar array kicks up dust that settles on the array's panels. A habitat's thermal radiators must face away from the sun, but cannot face toward the reactor's exclusion zone. Construction equipment staging must be close enough to the habitat for efficient crew access, but far enough that vehicle traffic does not contaminate airlock approaches with additional dust. This terrain bottleneck means that base layout is not simply an architectural choice. It is a constrained optimization problem where every placement decision affects power generation, dust contamination, thermal management, communication geometry, and crew safety simultaneously. Getting the layout wrong is not merely inefficient. It can mean that dust from one asset degrades another, that shadow from one structure reduces power to a neighbor, or that the exclusion zone for a future reactor forces a redesign of infrastructure that was already landed and positioned. On Earth, you can relocate a building if the site proves suboptimal. On the Moon, every landed asset stays where it touches down unless you have heavy equipment capable of moving multi-ton structures across regolith. Equipment that itself requires power, maintenance, and dust management. None of these constraints are secrets. NASA's own documentation describes them clearly. The agency's engineers are among the best in the world, and the phased approach reflects genuine awareness of the challenge. But the public narrative has raced ahead of the engineering reality. The $20 billion number sounds enormous until you compare it to the International Space Station, which cost over $100 billion in low Earth orbit, an environment that is dramatically easier to supply, service, and evacuate than the lunar surface. The three-phase timeline sounds methodical until you consider that each phase depends on political continuity, sustained funding, successful commercial partnerships, and the absence of catastrophic mission failures across a decade of operations. And the confident animations of gleaming habitats and roving astronauts look inspiring until you consider what those habitats must endure and what those astronauts must survive every single day. The moon base conversation needs a fundamental reframing, not because the goal is wrong. A permanent lunar presence would advance science, develop critical technologies for deeper space exploration, and expand human capability in ways that are genuinely worth pursuing. But because the difficulty is systematically underestimated in almost every public discussion, the moon is not Mars. It is closer, more accessible, more familiar. People see it in the sky every night. Astronauts have walked on it within living memory. It feels manageable. It feels like the obvious next step. That feeling is the trap. The moon is close enough that we can reach it in 3 days. But closeness does not make the surface hospitable. Closeness does not reduce the radiation. Closeness does not moderate the thermal extremes. Closeness does not make the dust less abrasive or the vacuum less lethal. Closeness simply means that when something goes wrong at the base, help is 3 days away instead of 9 months away. That is an advantage over Mars, certainly. But it does not change the fact that the environment itself attacks every human system with a ferocity that is difficult to appreciate until you examine the engineering in detail. What follows in the rest of this story is that examination. We will move through the specific physical burdens of the lunar surface, one by one, and show how each of them escalates when you shift from a short visit to permanent habitation. We will look at dust that behaves like no terrestrial material, temperature swings that crack metals and destroy electronics, radiation that accumulates silently in human tissue, power systems that must survive conditions they were never designed for, maintenance burdens that grow faster than any crew can manage, resupply chains so fragile that a single launch failure could threaten lives, and propose solutions that help but always create new problems somewhere else in the system. The moon is not waiting for us to arrive. It is already degrading the equipment we have sent ahead. The question is not whether humanity can build a moon base. Given enough time, money, and political will, we almost certainly can. The question is whether we understand what that base will actually demand once it exists. Because the answer to that question is where the real shock lives, and it begins with what covers every square inch of the lunar surface. Every astronaut who walked on the moon came back with the same warning: not about the vacuum, not about the isolation or the silence or the disorienting horizon, about the dust. Eugene Cernan, commander of Apollo 17, the last crewed mission to the lunar surface, stated bluntly that dust was one of the most serious problems encountered on the moon. Harrison Schmitt, a geologist and the only trained scientist to set foot on the surface, suffered an immediate respiratory reaction. The moment regolith particles entered the cabin, his nasal passages swelled, his throat burned, his sinuses clogged for hours. He described it as lunar hay fever, and every single one of the 12 people who walked on the moon experienced some version of this reaction during their brief stays. Brief. That is the word that should alarm anyone planning a permanent base. Apollo surface missions lasted between 22 and 75 hours. The longest single EVA was about 7 hours and 37 minutes. During those hours, dust accumulated on spacesuits so aggressively that astronauts could not remove it, even with dedicated brushing. It coated visors, reducing visibility. It clogged wrist joints and glove mechanisms, stiffening movement. It infiltrated every seal, every zipper, every interface between suit components. By the end of even the shortest moonwalk, the outer layers of spacesuits showed measurable abrasion. Boot soles wore down, fabric layers frayed, and once the astronauts returned to the cabin and repressurized, the dust they carried inside became airborne in the confined space, entering lungs, eyes, and equipment with no practical way to contain it. Apollo managed this because Apollo left. The crews returned to orbit within days. Their equipment was never required to function again on the surface. The spacesuits were retired. The landers were abandoned. Every piece of hardware that had been degraded by dust was simply left behind, a disposable cost of a short mission. A permanent base does not have that option. The suits must be reused hundreds of times. The airlocks must cycle thousands of times. The habitat must keep dust out across years of continuous operation. And this is where the nature of lunar regolith transforms from an inconvenience into a relentless operational enemy. Lunar dust is not like any dust on Earth. Terrestrial dust particles are rounded and smoothed by billions of years of wind erosion, water tumbling, and chemical weathering. They settle predictably. They can be swept, vacuumed, or washed away. Lunar regolith has experienced none of these processes. The moon has no wind, no water, no chemical weathering cycle. Its surface material is created entirely by impacts. For over 4 billion years, micrometeorites have been slamming into the lunar surface at speeds of tens of kilometers per second, pulverizing rock into fragments of every size. The smallest particles, those below 20 micrometers, constitute what scientists formally call lunar dust. These particles are not rounded. They are fractured, angular, jagged. Under electron microscopes, they resemble shards of broken glass rather than grains of sand. Their edges are sharp enough to cut biological tissue at the cellular level, but the shape is only the beginning of the problem. The moon's lack of atmosphere means the surface is continuously bombarded by solar wind, a stream of energetic charged particles flowing outward from the sun. This bombardment implants ions into the outer surfaces of regolith grains and strips electrons from their structures, leaving the particles electrostatically charged. On Earth, humidity in the air rapidly dissipates electrostatic charge. On the moon, there is no humidity. The charge persists indefinitely. Charged dust clings to any surface it contacts with a tenacity that mechanical brushing cannot overcome. It adheres to metal, glass, fabric, skin, and polymer coatings with roughly equal stubbornness. Apollo astronauts attempted to brush dust from their suits before re-entering the lunar module. The brushing removed perhaps half the visible material. The rest clung fast. The chemical composition adds yet another dimension. Lunar regolith is roughly 50% silicon dioxide by weight, with iron oxide and calcium oxide making up most of the remainder. But these oxides are not inert. The fracturing process that creates fine dust also exposes fresh mineral surfaces that have never interacted with oxygen or water. These freshly exposed surfaces are chemically reactive. When they encounter moisture, as they would inside a pressurized habitat containing human beings who breathe and sweat, they can generate free radicals, highly reactive molecular fragments that damage biological tissue. Research using lunar simulant dust has demonstrated that prolonged exposure destroys lung cells and brain cells in laboratory conditions. The particles are small enough to penetrate deep into the respiratory system, past the body's filtering mechanisms, and lodge in the alveoli where gas exchange occurs. Once there, they cannot be expelled. Their sharp edges and reactive surfaces cause chronic inflammation. The long-term health consequences of months or years of low-level lunar dust inhalation are genuinely unknown, because no human being has ever been exposed for that duration. But the existing evidence from Apollo, from simulant studies, and from analogous terrestrial exposures to fine silicate dust suggests the risk is serious. NASA is aware of this. The agency has been funding dust mitigation research for years. One promising technology is the electrodynamic dust shield, which uses alternating electric fields to lift and repel charged particles from surfaces. In March 2025, NASA successfully demonstrated this technology on the lunar surface using a small experimental unit delivered by a commercial lander. The shield removed dust from glass and thermal radiator surfaces with encouraging effectiveness. This is a genuine engineering advance, but it is also a narrow one. The dust shield protects specific flat surfaces. It does not protect spacesuit joints. It does not prevent dust from entering airlocks during crew transitions. It does not keep particles from accumulating in habitat ventilation systems or from grinding against mechanical seals during thousands of operational cycles. It is one tool against a problem that manifests everywhere simultaneously. The operational reality of dust management at a permanent base would look something like this. Every time a crew member exits the habitat for a surface excursion, they pass through an airlock. Dust enters the airlock. When they return, they attempt to clean themselves and their equipment before repressurizing. Some dust remains. It enters the habitat. Ventilation systems must filter this dust continuously using filters that themselves degrade under the abrasion. Those filters must be replaced regularly with filters that must be manufactured on the moon or launched from Earth. Mechanical equipment used outside, including rovers, drills, sample collectors, and construction machinery, accumulates dust on every moving part. Bearings grind down, optical sensors cloud over, electrical connectors develop resistance as dust works into contact surfaces. Each piece of equipment requires cleaning and maintenance at intervals that are shorter than anything designers would face on Earth. The base would need a dedicated dust management protocol, consuming a significant portion of crew time every single day. Not occasionally, not during special maintenance windows. Every day. The moon does not take days off from producing and mobilizing dust, and the dust is continuously replenished. Every footstep on the lunar surface kicks up particles that, in the low gravity and vacuum, travel far higher and settle far more slowly than they would on Earth. Vehicle traffic raises plumes that can travel kilometers before settling. Even without human activity, the electrostatic charge on dust particles causes a phenomenon called levitation, where fine grains are lofted above the surface near the terminator, the boundary between sunlight and shadow, as differential charging creates electric fields strong enough to lift particles against the moon's weak gravity. A base operating near this terminator environment, which is precisely where South Pole bases would be located due to the low sun angles, would face dust mobilization as a continuous background condition. There is no way to solve the dust problem. There are ways to manage it, but management is permanent. It never ends. And it competes for crew time, equipment resources, and spare parts with every other maintenance demand the base generates. Dust is not a hazard you overcome during construction. It is a tax you pay every day for as long as the base exists. The second enemy is temperature, and it wages war on every material and machine through a mechanism that is deceptively simple but devastatingly effective. Thermal cycling. We have already described the raw temperature ranges. At the lunar South Pole, sunlit surfaces can reach above 100 degrees Celsius, while shadowed areas nearby plunge below minus 170 degrees Celsius. But raw temperature is only half the story. The real damage comes from the transitions. When a piece of equipment moves from sunlight into shadow, or when shadow sweeps across a stationary structure as the sun shifts along the horizon, the temperature changes rapidly because there is no atmospheric buffer to moderate the transition. A surface that was baking at 100 degrees can begin plunging toward minus 100 degrees within minutes of losing direct sunlight. And then, when the sun returns, the temperature reverses just as sharply. This cycling creates thermal stress in every material. Metals expand when heated and contract when cooled. Different metals expand at different rates. A structure made of multiple materials, which every habitat and piece of equipment necessarily is, experiences differential expansion. Joints that were tight at one temperature become loose at another. Seals that held at 20 degrees Celsius develop gaps at minus 150 degrees. Welds that were sound at room temperature crack after hundreds of cycles between extremes. This is not theoretical. It is basic materials science, and it is one of the primary failure mechanisms for long-duration hardware in space. On the ISS, thermal cycling is already a significant maintenance concern, and the station orbits in an environment where the thermal range is smaller and the cycling period is roughly 90 minutes. On the lunar surface at the South Pole, the cycling period depends on local topography. Some sites experience slow cycles over days as the sun traces its shallow arc. Others experience rapid cycling as the sun dips behind nearby ridgelines and reappears, creating abrupt transitions between full sunlight and deep shadow separated by minutes rather than hours. Equipment deployed at these sites would experience thousands of thermal shocks per year, each one slightly loosening joints, slightly propagating cracks, slightly degrading seals. The absence of convective cooling makes thermal management even harder. On Earth, engineers routinely use fans and airflow to cool electronics and machinery. In vacuum, that option does not exist outside a pressurized volume. Heat can only be rejected through radiation, which requires large radiator surfaces facing empty space, or through conduction into the regolith, which is a poor thermal conductor. Cooling a habitat or a piece of machinery on the Moon requires dedicated radiator panels that must themselves survive dust coating, micrometeorite erosion, and thermal cycling. If radiator efficiency degrades because dust accumulates on the surface, heat builds up inside the system. Electronics overheat, mechanical systems seize. The cooling system itself becomes a maintenance burden requiring regular dust removal, which brings the problem full circle back to dust management, consuming crew time and resources. Heating during darkness periods presents the opposite challenge. When a South Pole site enters shadow, surface temperatures fall rapidly. Without an atmosphere to retain any warmth, every object on the surface begins radiating its thermal energy into space. Batteries lose capacity in extreme cold. Lubricants thicken and eventually solidify. Electronics can fail below certain temperature thresholds as solder joints contract and circuit board materials become brittle. Keeping a habitat and its supporting equipment warm through a shadow period lasting several Earth days requires continuous power for electric heaters, and that power must come from a source that does not depend on sunlight. This connects directly to the third and fourth enemies, because vacuum and power interact with temperature to create compounding problems that are worse together than any of them would be alone. Vacuum is the condition that makes every other problem on the Moon lethal. Dust would be unpleasant in an atmosphere but manageable. Temperature swings would stress materials but could be buffered by insulation and convection. Radiation could be partially scattered by atmospheric particles. On the Moon, vacuum removes every buffer. It is the absence of environment, the null condition that turns every engineering margin into a cliff edge. A pressurized habitat on the Moon must hold roughly 1 atmosphere of internal pressure against the external vacuum. This is a pressure differential of approximately 100 kilopascals across every square meter of the habitat wall. For a modest cylindrical module 4 meters in diameter, the outward force on the end caps alone exceeds 500,000 newtons. The structure must bear this load continuously, without fatigue, while also surviving thermal cycling, dust abrasion, radiation degradation of polymer seals and composite materials, and the vibration of internal machinery. This is achievable with current material science, but it requires over-design, inspection, and maintenance at levels far beyond typical terrestrial construction. The critical vulnerability is seals. Every habitat requires airlocks, windows, docking ports, cable pass-throughs, and equipment hatches. Each of these is a penetration in the pressure envelope, a potential leak point. On the ISS, air leaks are a recurring concern. Despite the station operating in microgravity, where mechanical stress on seals is lower than it would be on a surface where thermal cycling and dust intrusion are constant, the station has experienced multiple slow leaks that required months of detective work to locate and repair. One leak in the Russian Zvezdar module persisted for years, with the source initially identified after months of detective work, but secondary cracks continuing to appear and require management well beyond the initial diagnosis, requiring repeated ultrasonic inspections, temporary sealant applications, and the isolation of entire compartments while diagnostic work proceeded. The crew spent hundreds of cumulative hours managing that single leak. On the ISS, that time was absorbed by a crew of 6 to 7 people with regular rotation and resupply. On a moon base with 4 crew members, a single persistent leak of comparable difficulty could consume a quarter of the available crew time for months, displacing science, construction, and other maintenance. On the Moon, those leaks would be compounded by dust working its way into seal surfaces during every airlock cycle, and by thermal contraction opening microscopic gaps during cold periods. A habitat airlock on a permanently occupied base might cycle twice daily per crew member for surface excursions, equipment transfers, and rover access. For a 4-person crew, that is roughly 8 cycles per day, nearly 3,000 cycles per year. Each cycle allows a small quantity of dust to enter the seal mechanism. Each cycle flexes the seal material through a pressure differential. Each cycle occurs against a background of thermal stress that may be expanding or contracting the seal housing depending on the time of day. After 1,000 cycles, the seal surfaces have experienced 1,000 abrasion events, 1,000 pressure flexions, and hundreds of thermal shocks. No airlock seal in the history of human spaceflight has been tested under these combined conditions at this frequency and duration. The expected service life of these components under actual lunar conditions is an open engineering question, and the answer determines how many replacement seals the base must stock and how often crew members must perform the painstaking task of replacing a pressure-critical interface. A slow leak on the Moon might not be immediately catastrophic. Habitats would carry reserve air supplies, but every leak represents lost atmosphere that must be replaced, either from stored reserves or from local production, if the base has operational water-splitting capability. Over months and years, the cumulative loss from slow leaks across dozens of seal interfaces could become a significant consumables drain, and the effort to locate and repair leaks, which on the ISS has sometimes required sealing off entire modules for weeks while engineers work through diagnostic procedures, would be far more disruptive at a smaller base with fewer habitable spaces and fewer crew members. Vacuum also means that any failure involving rapid decompression is immediately life-threatening. A puncture from a micrometeorite strike, a structural failure from fatigue crack propagation, an airlock mechanism jamming in a partially open state. Any of these events gives the crew minutes to respond before the habitat becomes uninhabitable. Emergency procedures would require immediate access to spacesuits and backup pressurized volumes. The base would need redundant sealed compartments so that losing one does not mean losing everything. This redundancy adds mass, complexity, and cost to every habitat design. Beyond the direct lethality of decompression, vacuum creates a more subtle long-term problem. Materials behave differently in vacuum than in atmosphere. Lubricants outgas, losing volatile components that provide their essential properties. This is not a minor technical footnote. It is a constant degradation process that affects every mechanical system with moving parts. On Earth, lubricants are formulated to operate in air, where oxygen and moisture help maintain their chemical stability. In vacuum, the volatile organic compounds that give lubricants their viscosity and film-forming properties escape into space molecule by molecule. The lubricant gradually becomes thicker, less effective, and eventually ceases to function. Aerospace-grade vacuum lubricants exist, but they are more expensive, less effective across wide temperature ranges, and still degrade over time. A rover joint that operates smoothly during its first month on the surface may begin seizing by month 6 as its lubricant outgasses and dust infiltrates the bearing. Replacing lubricant in a mechanical joint on the moon requires an EVA, which means radiation exposure, dust contamination of the crew member's suit, airlock cycling that introduces more dust into the habitat, and hours of crew time consumed on a task that would take minutes in a terrestrial workshop. Polymers degrade under combined vacuum and radiation exposure, becoming brittle over time. The seals, gaskets, cable insulation, window coatings, and flexible connectors throughout a habitat are predominantly polymer-based. Under terrestrial conditions, these materials last decades. Under combined vacuum, ultraviolet exposure, charged particle bombardment, and thermal cycling, their service life shortens dramatically. Laboratory testing with simulated lunar conditions has demonstrated measurable embrittlement in common aerospace polymers within months. On a base that must operate for years, every polymer component is on a degradation clock that ticks faster than any Earth-based engineering experience would predict. Metals in contact with each other can undergo cold welding, where the absence of oxide layers in vacuum allows atomic bonds to form between touching metal surfaces, fusing components that were meant to move freely. This phenomenon has caused mechanism failures on satellites and space station hardware. Multiple satellite solar array deployment mechanisms have experienced cold welding between metallic hinge components after prolonged storage in vacuum, requiring engineers to redesign mating surfaces with anti-galling coatings for subsequent missions. On a lunar base, where moving parts include airlock hinges, rover joints, drill mechanisms, and construction equipment, cold welding is a persistent threat that requires careful material selection and surface treatment for every mechanical interface. Designers must either coat every mating metal surface with anti-welding treatments that themselves degrade over time, or accept periodic failures where components bond together unexpectedly and must be separated or replaced. All of these challenges converge on the fourth enemy, power. Because without continuous reliable power, nothing else functions. The habitat cannot maintain pressure. The thermal management system cannot reject heat or provide warmth. The dust mitigation systems cannot operate. The air recycling and water processing systems stop. Power is not one system among many. It is the foundation that every other system depends on. Losing power on the moon is not like losing power on Earth, where you light candles and wait for the utility company. Losing power on the moon means losing life support. The margins are measured in hours, not days. NASA's South Pole site selection was driven in large part by power considerations. The elevated ridgelines near Shackleton Crater receive sunlight for approximately 80 to 90% of the lunar year, far more than any equatorial site where the 2-week night would be unmanageable with solar power alone. But 80 to 90% is not 100%. Even the best South Pole sites experience shadow periods, and during those periods, the base must survive on stored energy or alternative power sources. The energy storage challenge for surviving lunar darkness has been described by researchers as probably the most demanding energy storage challenge in the exploration of the solar system. To understand why, consider the arithmetic. A minimal lunar base supporting 4 crew members requires continuous power for life support, thermal regulation, lighting, communication, computing, and essential equipment. Conservative engineering estimates place this baseline at roughly 25 to 30 kilowatts of continuous electrical power. Some analyses that include active thermal management for external equipment and partial ISRU operations push the figure closer to 65 kilowatts. Even using the lower estimate, sustaining 25 kilowatts through a shadow period of, say, 4 Earth days requires 2,400 kilowatt-hours of stored energy. The best lithium-ion batteries currently available for space applications store roughly 200 watt-hours per kilogram at the cell level. System-level energy density is lower once you account for packaging, thermal management, charge controllers, and structural mass. A realistic system-level figure is closer to 150 watt-hours per kilogram, To store 2,400 kilowatt hours at that density, the base would need 16,000 kilograms of batteries, 16 metric tons. Launched from Earth, landed on the lunar surface. That is roughly the payload capacity of an entire large lunar lander devoted to nothing but batteries for a single 4-day shadow period. And that assumes the batteries perform at full capacity in an environment where extreme cold reduces lithium-ion output by 30 to 50% unless the batteries themselves are heated, which consumes additional power from the reserves they are supposed to provide. This arithmetic is why researchers have called lunar night survival the most demanding energy storage problem in solar system exploration. No battery chemistry currently in production or advanced development can make the numbers work at acceptable mass. Regenerative fuel cells, which store energy as hydrogen and oxygen and recombine them to produce electricity, offer higher energy density than batteries but introduce mechanical complexity, consumable management, and failure modes that add to the maintenance burden. Every energy storage approach trades one constraint for another, and none of them eliminate the fundamental problem. Darkness on the moon lasts long enough to exhaust any chemically stored energy supply that can be practically delivered. This is why NASA's moon base plan explicitly includes nuclear power. The Phase 2 timeline calls for radioisotope thermoelectric generators, known as RTGs, to demonstrate nuclear power capability on the surface. RTGs convert the heat from decaying radioactive isotopes into electricity. They are proven technology, having powered deep space missions for decades. But they produce relatively small amounts of power, typically in the range of hundreds of watts rather than the tens of kilowatts a base would require. For continuous operations, NASA envisions eventually deploying a fission reactor on the lunar surface capable of producing at least 10 kilowatts of electrical power, enough to sustain basic life support and operations through extended darkness. A lunar fission reactor is within engineering capability. NASA and the Department of Energy have been developing the kilopower reactor concept and its successors for exactly this purpose. But a reactor on the moon introduces its own complications. It requires a radiation exclusion zone around the reactor site, which early analyses suggest could be reduced to approximately 90 meters with proper regolith shielding, but which still constrains base layout. It requires cooling, which on the moon means radiator panels subject to the same dust and thermal cycling problems as every other surface system. It requires maintenance, which means either building the reactor to be extraordinarily reliable for years without servicing or designing it for robotic or crew maintenance, in an environment where every maintenance task is harder than it would be on Earth. And it requires political and regulatory approval to launch nuclear material, which adds programmatic complexity and potential delays. Solar power remains part of the plan, especially for Phase 1 and early Phase 2 when nuclear systems are not yet deployed. But solar panels on the moon face the same enemies as everything else. Dust accumulates on panel surfaces, reducing output. Electrodynamic dust shields can help, but they add complexity and power consumption of their own. Thermal cycling stresses panel mounting structures and electrical connections. Radiation degrades photovoltaic cell efficiency over time. And the low sun angles at the South Pole mean panels must be oriented nearly vertically and tracked to follow the sun's slow arc along the horizon, requiring mechanical tracking systems that are themselves vulnerable to dust and thermal stress. The power problem illustrates a pattern that recurs throughout every aspect of lunar-based design. Each system required for survival creates its own maintenance and vulnerability burden. Power systems need dust management. Dust management needs power. Thermal control needs power and radiator surfaces. Radiator surfaces need dust management and thermal cycling resistance. Life support needs power and filtration. Filtration systems degrade from dust and need replacement parts. Every solution demands something from every other system, creating a web of interdependencies where a failure in one area cascades through others. This cascading interdependency is the signature characteristic of permanent lunar habitation. It is what distinguishes a moon base from any engineering project in a more forgiving environment. On Earth, if your air conditioning fails, you open a window. If your power goes out, your house is still pressurized and breathable. If your water filtration needs maintenance, you drink bottled water for a day. On the moon, none of these fallbacks exist. Every system is critical. Every system depends on other systems. And every system is under constant attack from dust, temperature, vacuum, and radiation simultaneously. The 4 surface enemies described so far, dust, thermal extremes, vacuum, and power fragility, are the immediate, obvious challenges of operating on the Moon. They are the ones Apollo encountered in miniature during 3-day visits, and the ones any engineer designing lunar hardware must solve first. But they are also only the first layer of the problem. Beneath these surface-level burdens lie deeper threats that emerge only when habitation extends from days to months, from months to years. The human body begins to change in ways that partial gravity may not prevent. Mechanical systems enter fatigue regimes that short missions never reach. Maintenance backlogs accumulate faster than small crews can address them, and the supply chain connecting the base to Earth reveals its terrifying fragility when a single missed delivery can mean the difference between routine operations and survival crisis. The surface war is real, and it is punishing. But what comes next reveals why the true difficulty of a moon base is not surviving the environment for a mission. It is surviving the compounding failure of everything, all at once, with no easy way out. The enemies described so far are visible. You can see dust on a spacesuit. You can measure a temperature swing with a thermometer. You can watch a pressure gauge dropping during a leak. The enemies that come next are quieter. They work inside human tissue, inside fatigue cracks too small to inspect, inside logistics spreadsheets where a single missed line item cascades into crisis. They are the threats that emerge only when habitation extends beyond the time frame of any mission humanity has ever attempted on the lunar surface. And they are the threats that transform a moon base from a difficult engineering project into something closer to a permanent emergency. Radiation on the Moon is not an event, it is a condition. On Earth, the average person receives roughly 2 to 3 millisieverts of background radiation per year from natural sources. Airline pilots, who fly at altitudes where atmospheric shielding is thinner, accumulate perhaps 5 to 6 millisieverts annually. Astronauts aboard the ISS, protected by Earth's magnetic field and the residual shielding of low Earth orbit, receive between 150 and 200 millisieverts per year. On the unshielded lunar surface, the continuous dose from galactic cosmic rays alone reaches approximately 400 millisieverts per year. That number comes not from models but from direct measurement. China's Chang'e 4 lander carried a dosimeter that recorded the first ever surface radiation data in 2019 and 2020. The readings confirmed what transport calculations had predicted. The Moon's surface receives roughly 2 to 3 times the radiation dose experienced in low Earth orbit. 400 millisieverts per year is a number that requires careful interpretation. It does not cause immediate illness. Acute radiation sickness begins at doses above roughly 700 millisieverts delivered over a short period. The galactic cosmic ray dose is chronic, accumulating slowly at a rate of about 46 microsieverts per hour. The danger is not that a crew member will collapse from radiation poisoning on a Tuesday afternoon. The danger is cumulative biological damage. At 400 millisieverts per year, an astronaut stationed on the lunar surface for 18 months would accumulate 600 millisieverts, approaching NASA's career exposure limit. The biological consequences of this exposure include elevated cancer risk, increased probability of cataracts, potential damage to the central nervous system, cardiovascular degeneration, and possible heritable genetic effects. These are not speculative concerns. They are documented outcomes from epidemiological studies of radiation-exposed populations and from laboratory experiments using particle beams that simulate the galactic cosmic ray spectrum. But galactic cosmic rays are the predictable component. The unpredictable component is far more dangerous. Solar particle events occur when the Sun ejects massive bursts of energetic protons during solar flares or coronal mass ejections. These events are sporadic. They cannot be reliably predicted more than a few hours in advance, and they vary enormously in intensity. A modest solar particle event might deliver a dose equivalent to a few days of additional galactic cosmic ray exposure. A major event, comparable to the August 1972 event that occurred between the Apollo 16 and Apollo 17 missions, could deliver several sieverts to an unshielded person on the lunar surface within hours. That is a lethal dose. If the Apollo 17 crew had been on the surface during that event, rather than safely on Earth, they likely would have died. This is not a historical curiosity, it is a design constraint. A permanent moon base must have radiation shelter capability that is accessible to every crew member within minutes of a solar particle event warning. The shelter must provide enough shielding mass to reduce the dose from a major event to survivable levels. How much shielding is enough? Calculations vary, but most analyses converge on roughly 80 centimeters of lunar regolith, or an equivalent mass of alternative material, as the minimum needed to attenuate the most dangerous components of a large solar particle event. That thickness also significantly reduces the chronic galactic cosmic ray dose, though it cannot eliminate it entirely, because the highest energy galactic particles can penetrate meters of solid material. 80 centimeters of regolith shielding sounds manageable until you consider what it means operationally. Either you bury the habitat underground, which requires heavy excavation equipment capable of operating in vacuum, dust, and thermal extremes, or you pile regolith on top of a surface habitat, which requires moving hundreds of metric tons of material using equipment subject to the same degradation mechanisms described earlier. Both approaches are feasible in principle. Neither is simple, and neither has been demonstrated at any scale on the lunar surface. The excavation and regolith moving equipment must itself be launched from Earth, landed, deployed, and maintained all before the first crew arrives. There is also a subtlety that makes lunar radiation harder to shield against than deep space radiation. When galactic cosmic ray particles strike the regolith, they produce secondary radiation through nuclear interactions with the soil. Neutrons and gamma rays scatter outward from the impact point, creating an additional radiation component that comes from below and around the habitat rather than from above. A crew member standing on the lunar surface receives radiation not only from the sky but from the ground. A habitat sitting on the surface receives secondary neutron flux through its floor. Shielding the roof and walls is insufficient. The floor must also be shielded, or the habitat must be elevated above the surface with sufficient clearance, which creates structural and thermal challenges. This secondary neutron environment is an active area of research, and the contribution it makes to total dose depends on regolith composition, which varies from site to site. But it cannot be ignored in any credible base design. The radiation problem interacts with every other burden. Radiation degrades materials. Polymer seals become brittle under long-term radiation exposure. Solar panel efficiency decreases as radiation damages photovoltaic cells. Electronics can experience single-event upsets, where a high-energy particle strikes a transistor and flips a bit, causing software errors or hardware malfunctions. Radiation-hardened electronics exist, but are heavier, more expensive, and less capable than their commercial counterparts. A base relying heavily on commercial off-the-shelf components to reduce cost and mass would face higher rates of radiation-induced electronics failure than a base designed with full military-grade radiation. Hardening. Either choice imposes penalties somewhere in the system. Now consider what happens to the human body during a long stay on the moon, beyond the radiation effects. The moon's gravity is approximately 1/6 of Earth's. This is not zero gravity, it is partial gravity. And partial gravity is the great unknown of human space medicine. Decades of research on the ISS have documented what happens to the human body in microgravity. Bone density decreases at a rate of roughly 1 to 2% per month, concentrated in weight-bearing bones like the spine, pelvis, and legs. Muscle mass declines despite exercise protocols. Cardiovascular function shifts as the heart no longer needs to pump blood upward against full gravity, leading to cardiac atrophy and fluid redistribution toward the head. Vision degrades in a significant fraction of astronauts due to intracranial pressure changes, a condition called spaceflight-associated neuroocular syndrome. The immune system shows measurable suppression. Wound healing slows. These effects are well documented, extensively studied, and partially mitigated by rigorous exercise programs that occupy roughly 2 hours of every crew member's day aboard the station. The critical question for a moon base is whether 1/6 gravity is enough to prevent these changes. The honest answer is that nobody knows. No human being has ever spent more than 3 days in 1/6 gravity. Every data point we have comes from either full Earth gravity or near zero gravity in orbit. The region between those extremes the partial gravity regime where the Moon sits is a medical blank. Physiological models suggest that 1/6 gravity would slow the rate of bone and muscle loss compared to microgravity, but would not stop it entirely. The mechanical loading on bones at 1/6 gravity is dramatically less than on Earth. Walking on the Moon imposes roughly 1/6 the skeletal stress of walking on Earth. Whether this reduced loading is sufficient to maintain bone density over months and years, or whether it merely slows the decline to a rate that becomes dangerous over longer periods, is a question that can only be answered by actually putting people on the Moon for extended stays and monitoring their health. This uncertainty has consequences for base design. If 1/6 gravity proves insufficient to maintain crew health, the base must incorporate countermeasures, exercise equipment capable of providing loading equivalent to Earth gravity, possibly centrifuge-based systems that spin crew members to generate artificial gravitational force. These devices add mass, volume, power consumption, and mechanical complexity to a habitat already struggling with every kilogram and every watt. And the exercise time required, potentially 2 or more hours daily per crew member, competes with every other demand on crew time, including dust management, maintenance, scientific work, and construction. Psychological health presents another dimension of biological risk that worsens dramatically with duration. Apollo astronauts spent 3 days on the surface with constant communication with Earth and the psychological anchor of knowing they would return home within a week. ISS crew members spend 6 months in orbit, but enjoy real-time communication with family, periodic resupply missions that bring personal items, and the visual presence of Earth filling their windows. A Moon-based crew would be confined to a small pressurized volume for months, performing physically demanding and repetitive maintenance work, in an environment where a single mistake can be lethal, with Earth visible only as a small disk in the sky and communication delayed by only 1 1/3 seconds, but psychologically distanced by the knowledge that evacuation requires 3 days minimum. The isolation, confinement, monotony, and chronic danger create conditions analogous to Antarctic winter overstations and submarine deployments, both of which have documented rates of depression, interpersonal conflict, sleep disruption, and cognitive decline that increase with duration. The biological burdens compound. A crew member who is losing bone density, accumulating radiation dose, breathing trace amounts of dust that escaped filtration, sleeping poorly due to psychological stress, and spending 2 hours daily on mandatory exercise is not operating at full capacity. Cognitive performance declines under chronic stress and sleep disruption. Physical capability decreases as musculoskeletal deconditioning progresses. The very people who must maintain a complex life support system in a hostile environment are themselves being degraded by that environment. The base does not merely need to sustain human life. It needs to sustain human performance at the level required to keep the base functioning. If crew effectiveness degrades faster than anticipated, the maintenance burden that was already difficult becomes impossible. This leads to the third deep threat, maintenance itself. Every mechanical system has a designed operational life. On Earth, machinery operates in conditions where replacement parts are available, repair specialists can be called, and the environment, while sometimes harsh, does not simultaneously attack every component through vacuum exposure, thermal cycling, abrasive dust, radiation degradation, and electrostatic contamination. On the Moon, every one of those attack vectors operates continuously, and the result is accelerated wear on every system. The ISS provides the closest available analogy, and its maintenance record is sobering. The station requires constant attention from its crew. Astronauts spend a significant fraction of their working hours performing maintenance, replacing failed components, troubleshooting malfunctioning systems, and conducting emergency repairs. The station's environmental control and life support system, designated ECLSS, is one of the most maintenance-intensive assemblies ever built. Its water recycling system, air revitalization system, and carbon dioxide removal system each require regular replacement of consumable components, periodic deep maintenance, and occasional emergency intervention when failures occur. And the ISS operates in microgravity, where there is no dust infiltration, no thermal cycling as severe as the lunar surface, and no regolith abrading every external component. To understand how demanding this maintenance actually is, Consider what the ISS life support system requires just to keep functioning normally. The water recovery system processes urine and humidity condensate back into drinkable water. Its distillation assembly contains a rotating drum, fluid lines, filters, and valves that must be serviced regularly. The catalytic reactor that purifies the reclaimed water requires periodic replacement of its catalyst bed. The entire assembly has experienced repeated failures throughout its operational life, including pump malfunctions, separator drum issues, and contamination events that force the crew to switch to backup water supplies while engineers on Earth work through troubleshooting procedures that sometimes took weeks. The oxygen generation system uses electrolysis to split water into breathable oxygen and hydrogen. Its cell stack, the core component where the splitting occurs, degrades over time and must be replaced. The hydrogen it produces must be vented or recombined with carbon dioxide to reclaim additional water, a process that requires its own separate hardware called the Sabatier reactor. That reactor has its own maintenance schedule, its own failure modes, and its own history of breakdowns requiring crew intervention. The carbon dioxide removal assembly uses chemical beds to scrub CO2 from the cabin air. These beds must be regenerated by heating, which requires power and generates waste heat that must be managed. The beds degrade over time and must be replaced. The valves that cycle between beds have failed repeatedly over the station's lifetime, sometimes requiring emergency workarounds to maintain breathable air quality, while replacement parts were delivered on the next resupply mission. Each of these systems demands attention from a crew that also must maintain power generation, thermal control, communication, guidance and navigation, docking systems, exercise equipment, personal hygiene systems, food preparation equipment, and the station's structural integrity. The ISS crew typically devotes between 25 and 40% of its working hours to maintenance and repair, depending on what has broken recently. During periods of heavy maintenance, that fraction has climbed above 50%, leaving minimal time for the scientific research that justifies the station's existence. Now, translate this to the Moon. A lunar base would need all of the same life support functions. It would need the same water recycling, air revitalization, carbon dioxide removal, and waste processing systems or their equivalents. But every one of those systems would operate in an environment that accelerates degradation. Air filters would clog faster because of dust that no amount of airlock protocol can fully exclude. Water lines would be at greater risk of contamination from regolith particles. Valve seats and pump seals would wear faster because of abrasive particulate contamination. Electronics throughout every system would experience higher radiation-induced error rates. And all of this maintenance would be performed by a crew of 4 to 6 people, rather than the 6 to 7 on the ISS, with no possibility of sending a broken component back to Earth for analysis, and no ability to receive replacement parts faster than the next scheduled resupply. Beyond internal systems, the lunar base adds an entire category of external maintenance that the ISS largely avoids. Solar panels, thermal radiators, communication antennas, rover mechanisms, and construction equipment all sit exposed on the surface, accumulating dust, enduring thermal cycling, and degrading under radiation. Inspecting and servicing these assets requires EVA sorties that expose crew members to the very hazards the habitat is designed to protect them from, while consuming hours that cannot be spent on internal repairs. Every external maintenance task generates its own secondary costs. Suit wear, airlock cycling, dust ingress, and radiation dose accumulation. The internal and external maintenance demands do not merely add together, they compete for the same finite crew hours. The maintenance arithmetic becomes grim with small crews. NASA's early base concepts envision crews of 4 to 6 people during initial occupation phases. These crew members must divide their time among scientific research, which is the primary justification for the base, construction and expansion tasks, physical exercise, rest, and maintenance. If maintenance consumes more time than planned, something else must give. In practice, scientific output is usually the first casualty, followed by construction progress. If maintenance demands grow large enough, the base enters a mode where the crew spends most of its time simply keeping existing systems running, with no capacity for expansion or science. This has happened on the ISS during periods of heavy maintenance, and the station has the advantage of a much larger crew, regular resupply, and the ability to return failed components to Earth for analysis. Consider what a realistic maintenance cascade looks like in concrete terms. Month 8 of continuous occupation. A dust-contaminated valve in the carbon dioxide removal system begins sticking intermittently. The crew notices rising CO2 levels during sleep periods and traces the problem to the valve. Replacing it requires partially disassembling the removal assembly, a procedure that takes 2 crew members roughly 6 hours. During that time, the base operates on a backup CO2 scrubbing system with lower capacity, which means the habitat must reduce crew activity levels to keep CO2 within safe limits. The other 2 crew members cannot perform their scheduled EVA to clean dust from the solar panel array because the base cannot afford to have anyone exerting themselves and producing additional CO2 while the primary scrubber is offline. The solar panels go uncleaned for an additional 3 days. Their output drops by a few %, which reduces the power margin for the thermal management system. The following week, a secondary coolant pump shows elevated vibration readings, suggesting bearing wear, likely accelerated by thermal cycling. The crew must now prioritize which repair to perform first, knowing that the uncleaned solar panels are reducing their power budget and the bearing failure could cascade into a coolant system shutdown if left unaddressed. Every choice forecloses another option. Every repair displaces another task. The maintenance backlog grows. On the Moon, failed components cannot be returned for analysis. Spare parts must either be carried as inventory, manufactured locally, or improvised from available materials. Carrying sufficient spares for every system over a multi-year occupation requires either impossibly large initial payloads or frequent resupply missions, both of which are constrained by launch costs and vehicle capacity. Local manufacturing of spare parts, using techniques like 3-dimensional printing with lunar materials, is an area of active research but remains far from operational improvisation. The astronaut tradition of making repairs with whatever is available is possible for some failures but inadequate for others. A failed pressure seal cannot be improvised from duct tape and aluminum foil. A degraded solar panel cell cannot be repaired with a screwdriver. The maintenance burden also grows non-linearly with time. Mechanical systems that function flawlessly for the first 6 months begin showing wear at 9 months. By 12 months, multiple systems may need attention simultaneously. By 18 months, the base may be approaching the designed operational life of its earliest components, requiring either replacement or acceptance of degraded performance. This accumulation creates a maintenance backlog where the crew is perpetually behind, fixing systems that failed last week while knowing that other systems are approaching their own failure points. On a remote Antarctic station, a maintenance backlog is inconvenient. On the Moon, it is potentially lethal. The final deep threat is the one that connects everything else: resupply fragility. A permanent Moon base depends on a supply chain that stretches 240,000 miles from Earth's surface to the lunar South Pole. Every item the base cannot produce locally must travel that chain. Food, medical supplies, spare parts, replacement filters, new batteries, clothing, tools, scientific instruments, software updates loaded onto physical media, personal items for crew psychological health. Everything. The logistics of resupply are brutal. Launching 1 kilogram of payload to the lunar surface costs, by current estimates, between hundreds of thousands and over $1 million depending on the launch vehicle and lander used. A modest resupply mission delivering a few hundred kilograms of critical supplies represents a $100 million operation requiring months of planning, integration, launch, transit, and landing. The supply chain has no redundancy at the delivery end. There is no warehouse on the Moon. There is no secondary supplier around the corner. If a resupply mission fails during launch, which happens with non-trivial probability even for the most reliable rockets, or fails during landing, which has happened to multiple lunar landers in the 2020s, the base simply does not receive those supplies. The next opportunity may be months away. To appreciate the scale of the consumables problem, consider what a 4-person crew actually consumes. On the ISS, each astronaut requires approximately 1.5 kilograms of food per day. Multiply by 4 crew members and 365 days, and the base needs roughly 2,200 kilograms of food per year, assuming no local food production capability. Water recycling systems on the ISS recover approximately 90% of water, but the remaining 10% is lost and must be replaced from delivered supplies. For a 4-person crew, that replacement water amounts to several hundred kilograms per year. Air losses from airlock cycling, minor leaks, and system consumption add hundreds more kilograms of oxygen and nitrogen that must be replaced unless the base has fully operational local production. Then add the consumable components of life support: filters for dust management, chemical beds for carbon dioxide removal, catalyst cartridges for water purification, membranes for oxygen generation. Each has a finite operational life measured in weeks or months, and each must be replaced with components that currently can only come from Earth. Add spare parts for mechanical systems: pump impellers, valve seats, seal assemblies, bearings, electrical connectors, circuit boards, sensor elements. The manifest for a single year of lunar base operation runs to thousands of individual line items, each one critical enough that its absence could degrade some aspect of base functionality. NASA's plan envisions resupply missions roughly every 6 months, using commercial lunar landers. Each lander can deliver a few hundred kilograms to the surface, depending on the vehicle. For a base consuming several metric tons of consumables and spare parts per year, this means multiple resupply missions annually, each one an independent opportunity for failure. If the base requires 4 resupply missions per year to remain fully stocked, and each mission carries a 5% failure probability, the chance that all 4 succeed in a given year is approximately 81%. Over 5 years of operations, the cumulative probability of experiencing at least one resupply failure approaches 65%. A resupply failure is not a theoretical edge case. It is a statistical near certainty over the operational lifetime of the base. This fragility becomes dangerous when combined with the maintenance burden. Suppose a critical life support component fails 6 weeks before a scheduled resupply. The crew must either repair it using available spares, operate the base in a degraded mode with reduced safety margins, or request an emergency resupply mission that may take weeks to months to organize and execute. During that interval, the crew lives with reduced capability in an environment that offers no forgiveness for reduced capability. There is no ability to step outside and breathe fresh air while the CO2 scrubber is offline. There is no alternative water source if the recycling system degrades. There is no hospital if a crew member develops a medical emergency that exceeds the base's limited treatment capability. Now, imagine a specific scenario in operational detail. Month 14. The most recent resupply mission, carrying replacement HEPA filters for the habitat dust filtration system and a spare pump assembly for the water recovery system, fails during its landing approach. The lander's descent engine underperforms, possibly due to a fuel valve malfunction, and the vehicle impacts the surface at a speed that destroys its payload. The base receives nothing. The next resupply window is 4 months away. The existing HEPA filters are already past their nominal service life, operating at reduced efficiency. Dust concentration in the habitat air begins rising gradually. The crew can mitigate this by reducing EVA frequency, which reduces dust ingress through the airlock but also halts external maintenance and construction. Meanwhile, the water recovery pump that was already showing early signs of bearing wear continues degrading without the spare assembly that was supposed to replace it. The crew must now manage declining air filtration and a degrading water system simultaneously with no replacement parts for either. They can restrict water usage to extend the pump's remaining life. They can wear respiratory masks inside the habitat to reduce dust inhalation. These are survivable compromises in the short term. Over 4 months, they are physically and psychologically punishing, and they accept a level of health risk that no space agency has ever deliberately imposed on a crew. The 3-day transit time from Earth to the Moon is often cited as an advantage over Mars, where transit takes 9 months, and it is an advantage. But 3 days is not 3 hours. An emergency on the ISS in low Earth orbit can be addressed by a returning crew within hours, using already docked escape vehicles. An emergency on the Moon requires 3 days minimum for any response to arrive, assuming a rescue vehicle is already prepared for launch, which it almost certainly would not be. In practice, a lunar emergency would more likely require weeks for an organized response. The crew must survive on their own resources until help arrives, or they do not survive at all. The resupply problem also constrains base growth. Every expansion of the base, every new module, every additional piece of equipment adds to the maintenance inventory and increases the volume of spare parts and consumables that must be delivered regularly. A base that grows faster than its supply chain can support becomes a base that is perpetually short of something. And on the moon, being short of the wrong thing at the wrong time is not an inconvenience. It is an existential threat. This is the pattern that makes a permanent moon base qualitatively different from any other human engineering project. The threats do not exist in isolation. They interact. Dust degrades seals, which creates leaks, which consumes atmospheric reserves, which increases resupply demands. Thermal cycling fatigues structural joints, which creates inspection requirements, which consumes crew time, which reduces maintenance capacity for other systems. Radiation degrades electronics, which causes system malfunctions, which creates repair tasks, which require spare parts, which depend on resupply missions, which are expensive and occasionally fail. Human health degrades from radiation, partial gravity, dust exposure, and psychological stress, which reduces crew effectiveness, which increases the time needed for maintenance, which competes with exercise that is needed to slow the health decline. Every burden feeds every other burden. The system is not merely difficult, it is reflexively hostile, constantly generating new problems from the interaction of existing ones. A short mission avoids this compounding entirely. You land, you perform your tasks, you leave before the interactions have time to develop. The dust has not yet worked its way through your seals. The thermal cycling has not yet fatigued your joints. The radiation has not yet accumulated to concerning levels. The crew is still fresh, motivated, and physically capable. The supplies you brought are still adequate. Everything works because nothing has had time to degrade. Permanence changes the equation completely. Permanence means living inside the compounding. It means watching every system gradually degrade while knowing that the degradation rate is faster than your repair rate, unless everything goes exactly according to plan. It means accepting that on the moon, things do not go exactly according to plan, because the environment finds every weakness in every system and exploits it continuously. The proposed solutions for these deep threats exist. Regolith shielding for radiation, exercise protocols for bone and muscle, psychological support programs for mental health, predictive maintenance algorithms for mechanical systems, redundant supply chains for logistics. Each solution is real, each is being actively researched, and each helps, but each also introduces its own demands on mass, power, crew time, and complexity. The solutions do not eliminate the threats, they trade them for different burdens. And the total burden of all solutions combined is what determines whether a permanent moon base is operationally sustainable or whether it collapses under its own weight. What comes next is an honest examination of those solutions, and what remains after the best engineering humanity can offer has been applied. The answer is not hopeless, but it is far harder than the animations suggest. The engineers working on the moon base are not naive. They have read the Apollo reports, they understand the dust, they have modelled the thermal cycles. They have calculated the radiation dose rates and mapped the shadow periods at every candidate South Pole site with resolution down to individual boulders. The solutions they propose are real, grounded in physics, and in many cases already under development. The question is not whether these solutions exist. The question is whether the total burden of implementing all of them simultaneously, in the same hostile environment, with the same constrained crew and the same fragile supply chain, adds up to something that human institutions can actually sustain. Start with the solution that generates the most optimism: water ice extraction. The permanently shadowed craters near the lunar South Pole contain water ice deposits that have been accumulating for billions of years, shielded from sunlight by crater walls that never see the sun. If this ice can be mined and processed, it transforms the logistics equation. Water means drinking supply without launching it from Earth. Electrolysis of water produces oxygen for breathing and hydrogen for rocket propellant. A base that can produce its own water, air, and fuel locally becomes dramatically less dependent on resupply from Earth. This concept, called In Situ Resource Utilization, or ISRU, is central to NASA's long-term moon base strategy. and arguably the single strongest argument for the South Pole location. The optimism is warranted in principle. In practice, every step of the ice extraction process confronts the same environmental hostility described throughout this story. The ice sits in permanently shadowed craters where temperatures hover below -200 degrees Celsius. Any equipment sent to extract ice must operate in these conditions. Conventional lubricants solidify, batteries lose most of their capacity, metals become brittle, electronics can fail as solder joints contract and circuit board substrates crack. The equipment must either carry its own heat source, which requires power, or be designed with exotic materials that maintain function at temperatures approaching those of deep space. Either approach adds mass, cost, and mechanical complexity. The ice itself is not a convenient frozen lake. Orbital observations suggest it exists as thin molecular deposits mixed into the upper layers of regolith, possibly concentrated in pockets, but distributed unevenly across crater floors. Extracting usable quantities may require excavating and heating large volumes of regolith to liberate water vapor, then capturing and condensing that vapor in vacuum conditions where water does not exist as a liquid at any temperature. The processing equipment must handle abrasive, electrostatically charged regolith without clogging, jamming, or wearing out. It must do this repeatedly, reliably, and at a scale sufficient to supply a base with hundreds of liters of water per month. No such system has been tested on the Moon. The engineering is plausible, the operational reality is unproven, and the extraction process creates its own power demand. Heating regolith to release water requires energy. Electrolyzing water into hydrogen and oxygen requires energy. Compressing, storing, and distributing those gases requires energy. The power budget for ISRU operations is substantial, and it competes with every other power demand at the base. If the base is relying on solar power during illumination periods and stored energy during shadow periods, the addition of ice mining to the power budget may push the system beyond its margins, unless nuclear power is already operational. This creates a sequencing problem. You need power to mine ice. You need ice to reduce your dependence on resupply. You need resupply to deliver the power systems. Each capability depends on the others, and the order in which they are deployed determines whether the base can sustain itself or whether it remains indefinitely dependent on Earth. Regolith shielding is the second major proposed solution, primarily for radiation protection. As discussed earlier, approximately 80 centimeters of regolith over a habitat reduces radiation dose to levels that permit longer occupancy. The concept is straightforward. The Moon's surface is covered in regolith. You do not need to launch shielding material from Earth. You simply pile local soil on top of your habitat. The execution is anything but straightforward. 80 centimeters of regolith over a habitat module, several meters in diameter and 10 or more meters long, represents dozens of metric tons of material that must be excavated, transported, and placed with sufficient precision to provide uniform coverage without damaging the underlying structure. This requires construction equipment, excavators, haulers, and placement mechanisms capable of operating in vacuum, thermal extremes, and pervasive abrasive dust. The equipment must be launched from Earth, landed, deployed, and commissioned before the shielding work begins. Each piece of construction machinery is subject to the same degradation mechanisms that threaten every other surface system. Bearings grind, seals leak, optical sensors cloud over. The machines themselves require maintenance, spare parts, and power. Some researchers have proposed sintering regolith, using focused solar energy or microwave radiation to fuse loose soil into solid building blocks that can be stacked around habitats. This approach has been demonstrated in laboratories using lunar simulant materials and shows genuine promise. Sintered regolith blocks are structurally sound, provide radiation shielding, and offer some thermal insulation. But the sintering process requires equipment that must be designed for the lunar environment, consumes significant energy, and produces blocks at rates that make covering a full habitat a project measured in months rather than days. The equipment must handle the same abrasive, electrostatically charged feedstock that damages every other machine on the surface. And sintering does not eliminate the dust problem. It reorganizes dust into blocks while generating additional fine particles during excavation and handling. Robotics and autonomous systems represent the third major category of proposed solutions. The logic is compelling. If the lunar environment is too hostile for continuous human exposure, use robots for the most dangerous and repetitive tasks. Robotic excavators can mine regolith and pile shielding. Robotic rovers can inspect external systems and clean solar panels. Autonomous maintenance systems can monitor habitat conditions and perform routine adjustments without crew intervention. NASA's moon base plan includes extensive robotic precursor missions during Phase 1 specifically to test these capabilities before human crews arrive. Robots help, but robots on the moon face every physical challenge that humans face, minus the biological vulnerabilities, plus their own set of limitations. Robotic systems require power. They require communication links to operators, whether those operators are on the moon or on Earth. Earth-based teleoperation involves a round-trip signal delay of approximately 2.5 seconds, which makes real-time control of delicate tasks difficult. Autonomous operation requires software sophisticated enough to handle unpredictable terrain, unexpected equipment states, and novel failure modes without human judgment. Current autonomy capabilities are impressive for structured environments like factory floors, but limited in unstructured environments like a construction site on an alien surface covered in electrostatically charged abrasive powder. Robots on the moon also suffer from dust, thermal cycling and radiation. Their joints stiffen as lubricants degrade, their sensors become occluded by dust accumulation, their electronics experience radiation-induced errors, their batteries lose capacity in extreme cold. A robot that requires human maintenance every few weeks provides less net benefit than it initially appears because the maintenance time it saves on one task is partially consumed by the maintenance it demands for itself. The net gain is positive but smaller than intuition suggests, and it depends critically on how reliable the robots prove to be in actual lunar conditions. A question that Phase 1 missions are specifically designed to answer, but have not yet answered. Nuclear power is perhaps the most credible long-term solution for the energy problem. A fission reactor on the lunar surface could provide continuous power through shadow periods, independence from solar illumination angles, and sufficient capacity to support both life support and ISRU operations simultaneously. NASA's development programs for compact space-rated fission reactors have been underway for years, and the technology is approaching readiness for a lunar demonstration. But nuclear power on the moon carries constraints that are easy to overlook. The reactor requires a radiation exclusion zone. With proper regolith shielding, this zone can be reduced to roughly 90 meters, but it still means the reactor cannot be adjacent to the habitat. Power must be transmitted across this distance, which requires cabling or wireless power transfer systems that are themselves exposed to the surface environment. The reactor requires cooling, and cooling in vacuum means radiator panels. Those panels must be large enough to reject the reactor's waste heat efficiently, and must survive dust accumulation, thermal cycling, and micrometeorite erosion for the reactor's operational lifetime, which is ideally measured in years. If radiator efficiency drops because of dust coating, the reactor must reduce output or risk overheating. Maintaining reactor cooling becomes yet another entry in the base's already overwhelming maintenance schedule. The reactor also represents a single point of failure unless the base deploys multiple units for redundancy, which multiplies the mass, cost, and maintenance burden. A single reactor failure during a shadow period, when solar power is unavailable, could leave the base without power for life support. Backup energy storage must be sufficient to sustain the crew through the time required to either restart the reactor or wait for solar illumination to return. This backup requirement partially negates the advantage of nuclear power because the base still needs substantial battery capacity for contingency scenarios. And there is the programmatic reality. Launching a nuclear reactor to the moon requires political approval, regulatory compliance, and public acceptance that are not guaranteed even when the technical case is sound. The history of nuclear power in space includes both successes and controversies. RTGs have powered deep space missions reliably for decades, but every launch carrying radioactive material generates public scrutiny. A fission reactor is a larger step, both technically and politically, and delays in approval could push the power solution past the timelines that the rest of the base plan depends on. The phased construction approach that NASA has adopted is itself a form of solution. By building capability incrementally, testing each system before committing human lives to it, and learning from each mission before planning the next. The agency reduces risk at each stage. This is sound engineering practice. It is how complex systems should be developed. The three-phase plan, from robotic scouting through infrastructure deployment to sustained habitation, respects the reality that lunar surface operations involve unknowns that can only be resolved through actual experience. But phased construction has its own vulnerability: time. The plan stretches across a decade. It depends on sustained political commitment through multiple election cycles, consistent funding from a Congress that has historically been unreliable in sustaining long-term space programs, successful execution by commercial partners whose financial viability is not guaranteed, and the absence of catastrophic mission failures that could trigger political retreat. This is not a hypothetical risk. It has happened before, to a program that was in many ways the direct ancestor of the current moon base effort. In 2004, NASA announced the Constellation program, an ambitious plan to return humans to the moon by 2020, using a new family of launch vehicles called Ares 1 and Ares 5, a new crew capsule called Orion, and a lunar lander called Altair. Constellation was funded, staffed, and actively developing hardware. Billions of dollars flowed into contracts. Test articles were built. Engine tests were conducted. The program had political support, congressional authorization, and a clear technical roadmap stretching across the decade. By 2009, 5 years and roughly $9 billion into the effort, an independent review committee concluded that Constellation was significantly underfunded relative to its goals and could not achieve a crewed lunar landing on any realistic timeline without major budget increases. In 2010, the incoming administration cancelled Constellation entirely. The Ares rockets were abandoned, the Altair lander was cancelled, only the Orion capsule survived, repurposed years later for the Artemis program. $9 billion of development work, 5 years of institutional momentum, and thousands of engineering careers were redirected or dissolved. The moon receded from NASA's operational horizon for over a decade. The parallels to the current moon base plan are uncomfortable. A decade-long phased construction program, billions in committed funding, commercial partnerships whose financial health depends on continued government contracts, a technical timeline that requires every phase to succeed before the next one can begin, and a political environment where priorities shift with administrations, budgets face annual reauthorization battles, and a single high-profile failure can trigger a reassessment of the entire program. The Constellation cancellation demonstrated that even well-funded, technically active lunar programs are not immune to political discontinuity. The Moon Base Plan, announced in 2026, faces the same structural vulnerability. Its timeline extends through at least 2 presidential administrations beyond the one that initiated it. If any administration during that span decides to redirect funding toward Mars directly, or toward commercial space stations, or toward deficit reduction, or toward any other priority that competes with a multi-billion-dollar lunar infrastructure program, the base could stall exactly as Constellation did: partially built, enormously expensive, and ultimately abandoned. The ISS survived its multi-decade construction timeline because it had bipartisan support anchored in the geopolitical relationship with Russia. International partnership created mutual accountability that made cancellation politically costly for any administration. The moon base does not yet have an equivalent anchor. International partners are mentioned in NASA's plans, and several nations have expressed interest, but no binding international commitment of ISS scale exists for the moon base as of this writing. The program depends on domestic political will sustained across a decade, and the historical record suggests that domestic political will for decade-long space infrastructure programs is fragile. If funding is interrupted or redirected at any point during the decade-long build, the base could stall in an incomplete state, having spent billions without achieving sustained habitation. The hardware already landed on the moon would sit unused, degrading under the same dust, radiation, and thermal cycling described throughout this story. The commercial partnerships would dissolve, the engineering teams would disperse, and the next attempt to build a moon base would start not from where the previous effort left off, but from a position weakened by public skepticism that the effort can ever be completed. Each proposed solution, taken individually, is reasonable. Water ice extraction, regolith shielding, robotics, nuclear power, phased construction. Each addresses a real problem with a real engineering approach, but none of them eliminates the underlying difficulty. Each one helps, and each one costs. The costs are measured in mass that must be launched, power that must be generated, crew time that must be allocated, and complexity that must be managed. When you add the costs of all solutions together, the total burden is staggering. The base does not merely need a habitat. It needs a habitat plus a power plant, plus a radiation shelter, plus a dust mitigation system, plus a thermal management system, plus ice mining equipment, plus construction robots, plus a maintenance infrastructure, plus a resupply chain, plus medical facilities, plus communication relays, plus rovers, plus spare parts for every one of these systems, plus the crew time to operate and maintain all of it simultaneously. This total system, with all its interdependencies, is what a moon base actually is. It is not a building, it is a machine. A machine with hundreds of subsystems, each dependent on the others, each under constant environmental attack, each requiring resources that compete with the needs of every other subsystem. Keeping this machine running is not a one-time engineering achievement. It is a continuous operational commitment that never ends for as long as the base is occupied. Consider the closest terrestrial analogy that exists: the Amundsen Scott South Pole Station in Antarctica. This facility supports a winter-over crew of roughly 50 people in one of the most hostile environments on Earth. Temperatures drop below -70 degrees Celsius. The station endures 6 months of continuous darkness. Resupply is possible only during the brief Antarctic summer. The facility is entirely dependent on fuel deliveries for its power generators, and those deliveries must traverse one of the most logistically challenging supply routes on the planet. The station requires constant maintenance. Systems fail regularly. Crew members spend significant time on upkeep, and this facility sits on a planet with breathable air, manageable radiation levels, full gravity, liquid water beneath the ice cap, and the possibility of emergency evacuation by aircraft during summer months. The Moon offers none of those advantages. The radiation is worse. The vacuum is lethal. The dust is destructive. The gravity is insufficient for long-term human health. Emergency evacuation requires days rather than hours, and the resupply route is not a 1,000-mile traverse across Antarctic ice. It is a 240,000-mile journey through space requiring a rocket launch, a 3-day transit, and a precision landing on terrain that has destroyed multiple robotic landers in recent years. If sustaining 50 people at the South Pole on Earth is one of the most demanding logistics operations in human civilization, sustaining even 4 people at the South Pole of the Moon is an order of magnitude harder. This is the reality that the press conferences do not convey, not because the engineers are hiding it. They are not. The technical documents are public. The challenges are described in NASA's own literature. But the public narrative, the one driven by animations and press events and social media enthusiasm, compresses the difficulty into a word like ambitious or challenging, and then moves on to the inspiring vision of what the base will achieve. The vision is genuine. The science that a permanent lunar base could produce is extraordinary. The technologies it would develop are applicable to Mars and beyond. The symbolic achievement of humanity sustaining itself on another world has meaning that transcends engineering. But the meaning does not reduce the difficulty. And the difficulty is what this story has been about from the beginning. Not to argue that a moon base should not be built. Not to suggest that the engineers are wrong to try, but to make visible the gap between what the public imagines and what the physics demands. Because that gap is where the real story lives. A moon base is not a destination that you build and then inhabit, the way you build a house and then move in. A house on Earth exists in an environment that passively supports human life. The air is breathable. The temperature is survivable. The structure holds itself up under normal conditions without active intervention. A moon base exists in an environment that actively opposes human life through every mechanism at its disposal. The air must be manufactured and recycled. The temperature must be actively managed every second. The structure must resist decompression under perpetual mechanical stress. The dust must be fought daily. The radiation must be shielded against continuously. The power must never fail. The supplies must keep coming. The moon is 240,000 miles away. You can see it from your backyard on a clear night. It looks serene. It looks like a place you could walk on, set up a tent, gaze back at Earth and feel a sense of accomplishment. Apollo proved that you can visit it and come home safely. That achievement is one of the greatest in human history. But visiting and living are not the same thing. Visiting means surviving the environment long enough to leave before it defeats your systems. Living means fighting the environment forever, because the environment does not pause, does not relent, does not forgive a missed maintenance cycle or a degraded seal, or a supply shipment that failed to launch on time. The moon is close enough that it seems manageable. That closeness is an illusion created by familiarity. We have looked at it every night of our lives. We have sent 12 people to its surface and brought them all back. We have photographed it, mapped it, studied its geology, and named its craters. It feels known. It feels like the obvious next step, but known is not the same as hospitable, and close is not the same as easy. The moon turns every ordinary human need into an extraordinary engineering problem. Breathing becomes a filtration and recycling challenge. Drinking becomes an ice mining and water processing operation. Staying warm becomes a nuclear power and thermal management project. Walking outside becomes a radiation exposure and dust contamination event. Repairing a broken pump becomes a spare parts inventory and crew time allocation crisis. Sleeping becomes a psychological support and circadian rhythm intervention. Nothing is simple. Nothing is passive. Nothing is free. And the most unsettling truth is that these problems do not shrink with time. They grow. The longer a base operates, the more its systems degrade. The more its systems degrade, the more maintenance it requires. The more maintenance it requires, the less time is available for the work that justified building the base in the first place. A base that cannot keep up with its own deterioration rate is a base that is slowly losing a war of attrition against the lunar environment. Winning that war requires not a single heroic engineering effort, but a permanent institutional commitment to staffing, funding, supplying, and maintaining an outpost on a world that erodes everything humans bring to it. That commitment is the true cost of a moon base. Not $20 billion, although that number is real and probably an underestimate. Not a decade of construction, although that timeline is real and probably optimistic. The true cost is the permanent obligation to keep fighting, to keep sending supplies, to keep replacing components, to keep training crews, to keep funding operations, to keep solving problems that the moon generates faster than intuition predicts. The base does not become self-sustaining after construction is complete. Construction is never complete. The base is always under construction, always under repair, always one system failure away from crisis. This does not mean humanity should not build a moon base. It means humanity should understand what building one actually requires, not the sanitized version with gleaming habitats and smiling astronauts. The real version, where every day is a system's fight against dust that infiltrates everything, darkness that kills power, radiation that accumulates in every cell, cold that cracks every seal, and distance that makes every missing spare part a potential emergency. The moon is not waiting to welcome us. It is waiting to test whether we can endure a permanent war against an environment that punishes human presence through every mechanism physics allows. The 12 astronauts who walked on the moon stayed for hours. They were the bravest human beings of their generation. They faced risks that most people cannot comprehend, and they left before the moon could show them what it truly does to things that stay. A permanent base would learn that lesson. Every cracked seal, every clogged filter, every degraded solar cell, every centimetre of bone density lost, every supply manifest scrutinized for the one missing item that could become a crisis. That is the moon base that physics demands. Not the one in the animations, the real one, and the real one is far worse than you think.